Swayam Prabha. Digital India. Educated India.
Today we will solve some numerical problems for shape memory alloys. So, here we will be using the constitutive relations that we have dealt with so far. Here is the first problem. It says that we have a shape memory alloy wire and the wire is fixed at one end and free at other end, and its dimensions are given. So, we have a wire like this, it is free at one end and fixed at other end, its dimensions are given, and the free end has a weight and the weight is 1 kg, the weight is also given. Now, the wire is at a temperature of 15 degree centigrade in martensite phase, and then we start heating the wire up to 77 degree centigrade, and then we cool down to a temperature of 20 degree centigrade. So, we have to find out the tip position of the wire at 74 degree centigrade during heating and 48.5 degree centigrade during cooling. Now, the weight of the wire remains same and there is no constraint here. So, the weight of the, because the weight of the wire remains same, the stress is also constant. So, at a constant stress all the heating and cooling is happening. So, first we have to find out the stress. So, the stress here we can call it sigma 0, initial stress, and that is the load. The load is 1 kg multiplied by 9.81. So, that becomes Newton divided by the area, and the area is pi by 4 multiplied by the diameter square, and the diameter is 0.31 into 10 to the power minus 3. So, if I square it I get the area and it gives it's in Newton per meter square. So, finally, the stress that comes is 86.046 megapascal. Now, at this stress, if I want to find out the tip stress, I have to just find out the strain, and accordingly if I want to find out the tip position, I have to just find out the strain, and accordingly I can find out the tip position. Now, before that let us see few things. This is our phase diagram, that is how it looks like. This is the temperature axis and this is the stress axis, and the entire diagram looks like this. We can at the lowest temperature is MF, then we have MS, and then we have AS, and then we have AF, and the slopes of the lines are given. So, we have CA and CM, and please note that here CA and CM are different, although as per the drawing it may look same, but please ignore the fact and please understand that they are different here. Now, we are operating at a stress of 86.046 megapascal. So, which means we are somewhere here maybe. So, at this constant temperature, constant stress, all the heating and cooling is happening. So, everything is happening along this dashed line, and this stress is 86.046 megapascal. So, we have 86.046 megapascal. So, we have to find out the characteristic temperatures at this stress. So, let us find out MF star. So, MF star is MF plus sigma by Cm. MF is given to me, sigma I have found out, Cm is also given to me. So, if I put all the values, the MF value comes to be 47.0 87 degree centigrade. And then we have ms star, which means ms at that value of sigma. So, we may denote this as mf star, ms star, as star, af star. So, ms star is again ms plus sigma by Cm, and the value comes to be 50.67 degree centigrade. Similarly, I can find out the value of as star. As star is as plus sigma by Ca, and this is 62.756 degree centigrade. And then we have af star, which is af plus sigma by Ca, and that comes as 75.756 degree centigrade. Now, the temperature at which the material is at the beginning is 15 degree centigrade. So, that is much less than mf star as well as mf. So, it is in this zone, and we have sigma critical S, which means the stress at which the stress induced martensite formation takes place, I mean start taking place, which means that detwinning start taking place, that is 138 megapascal, and it finish at 172 megapascal. So, our stress is 86, which is much less than sigma CRS. So, sigma CRS may be somewhere here and sigma CRF may be somewhere here. So, sigma CRS and sigma CRF. So, it is in the twin zone. The stress is less than sigma CRS and the temperature is less than mf or mf star. So, the material is in martensite condition. Now, if I want to find out the strain in the material at this temperature and at this stress, all I do is I just divide this sigma 0, the stress, by the Young's modulus at the martensite phase. So, epsilon at 15 degree centigrade is sigma 0 divided by Em. Em is given to us 20.3 gigapascal, and sigma 0 we have found out 86.046 megapascal. So, finally, the value comes to be 4.24 into 10 to the power minus 3. And then if I want to find out the deflection at this strain is the original length multiplied by strain. So, original length is given to us, and the original length is 0.3 meter. So, let us say this length we call it maybe L. So, it is L into sigma. So, the delta L is 1.272 millimeter, 1.272 millimeter. So, the total length is L plus delta L, and that comes to be 0.301272 meter. So, the tip position is at a distance 0.301272 meter from the fixed end, when at the initial stage when the material is at a temperature of 15 degree centigrade. Now, everything takes place along this dashed line. So, when the heating is taking place and the temperature is between A star and AF star, that time martensite formation process is going on. So, we are supposed to find out the tip position of the wire at a temperature of 74 degree centigrade, and 74 is between A star and AF star, because our A star is 62 and AF star is 75.756. So, 74 is in between that. So, when I want to find out my strain or the tip position, I need to take care of the fact that at that time martensite austenite formation is taking place. Then when we reverse it, when we cool down, we are supposed to find out the tip position at 48.5 degree centigrade, which means when we are between MF star and MS star, because MF star is 47.87 degree centigrade and MS star is 56.67 degree centigrade. That means, in between these two we have to find out the strain again. So, at that time we have to take care of the fact that at that time martensite formation is taking place. So, now we will first find out what is happening when we are at temperature 74 degree centigrade. So, to do that, we have to find out the amount of martensite fraction, and if I know that, that will give me rest of the quantities, and this we will do using both the Tanaka model and the Liang and Rogers model. Now, in Tanaka model, we model the variation of xi during the transformation as an exponential function, and in Liang and Rogers model it is modeled as a cosine function. Now, in both the cases, the starting and the end conditions are same. So, for example, when the austenite formation is taking place, the starting condition is xi equal to 0, xi equal to 1, and after the formation it is xi equal to 0. Similarly, during the martensite formation, at the beginning of the formation, xi is equal to 1 at the xi is equal to 0, and at the end it is xi equal to 1. So, both the models give the value of xi at the beginning and end, I mean the value of xi given by both the model agree to a great extent, but in between them, because one is modeling the variation as exponential function and the another is modeling the variation as cosine function, in between them the xi obtained from these two models are quite different, significantly different. So, let us first do it using the Tanaka model. So, as per Tanaka model, so at 74 degree centigrade, using Tanaka model, what we have is xi t is equal to e to the power a multiplied by a s minus t plus b a sigma 0. Now, a as per Tanaka model is natural log of 0.01 divided by a s minus a f, and that comes to be 0.3542 per degree centigrade, and B A as per Tanaka model is A by C A. C A is given to us and A we just calculated. So, B A is 0.0443 per megapascal of stress. So, if I find out xi here and if I put all the values here, so at T is equal to 74 degree centigrade, our xi comes to be 0.01867, 0.01867, and in percentage it comes to be 1.867%, which means that austenite formation is about to finish. Initially during the martensite, the martensite content was 100%, now it has reduced to 1.867%. So, at this same temperature, now if I find out the if I find out the martensite content using the Liang and Rogers model, then it comes to be as per the cosine rule that we know from the Liang and Rogers model. Now, here as per that model, xi t is equal to 1 by 2 multiplied by cosine of A t minus A s plus B A sigma 0 plus 1. Now, here A and B A differ, because as per the Liang and Rogers model it is pi by A f minus A s, and that comes out to be 0.242 per degree centigrade, and B A comes to be minus A by C A, and that is for this model minus 0.03021 per MPa. So, if I put these values at and I find out the xi at a temperature of 74 degree centigrade, then xi comes to be 0.0428, which in percentage is 4.28%. So, you can see that there is some difference between the xi's predicted by the Tanaka model and the Liang and Rogers model. Now that we have got the xi's, we have to now put the constitutive relation, put the xi in the constitutive relation and find out the strains. So, we know as per the constitutive relation that sigma minus sigma 0 is equal to epsilon of xi E of xi multiplied by epsilon minus epsilon 0 plus omega of xi multiplied by xi minus xi 0 plus this capital phi multiplied by t minus t 0. Now, this we neglect because the effect is much smaller as compared to the other two effects because of E and omega. Now, in this entire process sigma and sigma 0 are same, because we have seen that our load remains same and there is no constraint to it. So, sigma and sigma 0 are same. So, the left hand side is 0 and that leaves us with E as a function of xi multiplied by epsilon minus epsilon 0 plus omega as a function of xi multiplied by xi minus xi 0, and then we have E again as a function of xi multiplied by xi minus xi 0 minus epsilon L into E as a function of xi, because we know that omega is equal to minus epsilon L multiplied by E, and that entire thing multiplied by xi minus xi 0. So, and that right hand side is 0. Now, E as a function of xi is E A plus xi into E m minus E A, that we get from the rule of mixture. So, all I have to do is using the Tanaka's model, I have to find out xi at the desired temperature for the given constant stress, and once I get my xi, I can get my E. Once I get my E, I can get this quantity which is omega, and then I put in this equation that will give me epsilon. Then the similar thing we can do it Liang and Rogers model. Using that model we will find out xi, and again we will get E, we will get omega, we will put in this equation, and that will give us epsilon. So, let us do it using Tanaka's model. So, we can say strain calculation using Tanaka model. To do this, we have to find out our xi at that particular stress, at that particular temperature and stress. So, for that is already done by us, and the value that we got is 0.01867. So, for that particular xi, if I find out the E, then E comes to be E xi is, so when xi is equal to the value that I got 0.01867. So, for that xi our E is, so we do not need to write it E xi anymore. And that is 44.54 GPa. We are just using this equation and we are putting xi is equal to 0.01876. So, naturally omega becomes minus epsilon E, and that comes as minus 2.984 GPa. Then if we put this in this equation, if I put this quantity and this quantity in this equation with all the initial conditions taken care of, then we have 44.54 in GPa. Strain is unknown to me. The initial strain was 4.24 multiplied by 10 to the power minus 3, and then plus we have omega which is minus 2.984, and then we are multiplying that with xi minus xi 0. The xi at present is 0.01867 and xi 0 is minus 1, because initially the material was martensite, now it is becoming austenite gradually. Then if I solve this equation, then E comes to be minus 0.0615. So, that is the amount of strain it is experiencing at a temperature of 74 degrees centigrade. So, it is at T is equal to 74 degrees centigrade. Now that we know our epsilon, we can find out the strain, we can find out the elongation or contraction, which is delta L, and delta L is L multiplied by epsilon, and that gives me a contraction of 0.01845. So, and that is in meter, and then we can find out the final length, we can call it the L final, and that is L plus delta L, and then we get 0.2815, meter. So, we can say that now the tip position is at a distance 0.2815 from the fixed end. Now, we have to do the same thing using the Liang and Rogers model. So, now we will do strain calculation using Liang and Rogers model. So, here again our f's we got xi equal to, from this model the xi that we got is 0.0428, and then again if we apply the same formula, our stress is not changing, so it is 0, and then we have okay. So, at that xi we need to find out the E. So, E as per the same formula, EA plus xi into EM minus EA, that comes to be 43.94 GPa, and omega comes to be minus 2.944 GPa. Then if we apply the same procedure, same constitutive relation, the equation looks like this. And then we have plus omega, so it is minus 2.944 and then multiplied by 0.0428 minus 1. So, by solving we get our strain as minus of 0.0599, and then that gives me a delta L as epsilon multiplied by L, and we get that to be minus 0.01797 meter. So, L final, which means L plus delta L is 0.282 meter, and everything is at a temperature of 74 degrees centigrade. So, as per the Liang and Rogers model, at a temperature of 74 degrees centigrade, while the material is being heated, the tip position of the wire is at a distance of 0.282 meter from the fixed end. So, these are the two results predicted by these two models, and as we go closer to the austenite finish temperature AF star, the model will come to more and more agreement. And similarly, at the beginning closer to austenite start temperature, the results predicted would be very similar to. In between them there would be some variation, because as we said just now, one of the model is modeling the xi variation using exponential function, and another model is modeling the xi variation using cosine function. Now, the next job is to find out the variation of xi and then find out the strains and tip displacement during the cooling operation. So, that we will do in the next lecture. With this I would finish this lecture here. Thank you.